Okay, we talked a little bit in general about weather and what it is. So we got to have a reason why we have weather. Uh, where does the energy, where does the source of power for why we have weather? Well, that all comes from the sun. So we're going to talk a little bit about the sun, how that energy gets to us, and how it kind of comes in to play and how it also leaves the earth. So how does this energy flow into and out of this earth and this atmospheric system to maintain a stable planet? That's the really interesting part. Uh, we have various types of electromagnetic radiation. If you've seen a microwave, and I'm sure you all have, then that's one type of electromagnetic wave radiation, provides heat. Uh, if you put your hand above a hot stove or by a grill, you feel heat radiating out from it. That's electromagnetic radiation. X-rays. So there are different spectrums to electromagnetic radiation. Our thing we see in the visible spectrum, it's between the ultraviolet radiation and infrared radiation. So that's what we see. We're actually, when your eyes are looking out there and seeing it, you're seeing electromagnetic radiation. So what is it? It has a wavelength. I always think of it in terms of an ocean having a wavelength between waves. Well, electromagnetic radiation does as well. So when you get one crest, wait, it's going to go down, it's going to come back up. When it comes back up, that's the second crest. The distance between those two is the wavelength. That's all it is. And the closer the wavelengths are together, the more they're going to pass you. When I'm out in the ocean, when one's hitting right after the other, I can tell. Or when there's a nice slow swell to the waves, and you can sit on your raft and just sit there for a while. Also, interestingly, electromagnetic radiation moves at the speed of light. So, the frequency, the more frequent the waves are with electromagnetic radiation, the more energy they possess. All right, in meteorology, we like to make things as simple as possible. They're not, but we like to assume that everything is a black body. Well, what does that mean? Well, that means that every piece of energy coming from electromagnetic radiation is either absorbed by whatever that object is or retransmitted away. And most of it is, if you think about an electromagnetic black body, all the radiation is absorbed and then all is sent back out. Most surfaces approximate black bodies. It makes the laws simpler. So, notice it says here, Wend's displacement law. So the wavelength of the most intense radiation emitted by a black body is inversely proportional to its absolute temperature. Well, the sun is a whole lot hotter than Earth, right? So, therefore, the wavelength of the sun would be a lot shorter than the wavelength of Earth. And guess what? That's the case. So somebody did the physics and math correct. And interestingly, our eyes are adapted to see in the visible range, which is very close to where the maximum amount of electromagnetic radiation comes from the sun. All right. The other thing is the amount of energy that comes is temperature to the fourth power of whatever body it is that's emitting it. Well, the Earth has one temperature. The sun, way more. And then that sun's energy is to the fourth power. So there is a ridiculously amount more energy coming from the sun than there is from the Earth. Another interesting fact is, how far is the Earth from the sun? Well, we can use what we call the inverse square law. So 1 over the radius to the sun. If that was 1, which is Earth, we say Earth's radius, then 1 over 1, 1. However, if that was a 5, 1 over 5 squared is 1/25. So if you went out 5 times the distance of Earth from the sun, only 1/25 of the sun's energy would make it to you. All right, so now we've talked a little bit about the sun and how it is our energy source. You would think, oh, that makes it simple, right? Energy is the same everywhere on the Earth. No. The Earth is tilted. It's tilted 23.5 degrees. So that means, say you take a flashlight and you look it straight down. There would just be a tiny, very intense circle. Put that flashlight at an angle and you would cover a larger area and it wouldn't be as intense. You have the same amount of light or radiation is coming in. That happens on the Earth. At the equator, or in that area when the sun is directly overhead, you have the most intense radiation. Now, the further north or south you go, the more the tilt is. A matter of fact, in the winter, the North Pole, or in our summer, the South Pole, receives no radiation whatsoever. So you can see how the radiation distribution varies. The closer you are to the poles, the less radiation you're getting. The closer you are to the equator, the more radiation you get. And because the sun and the Earth, actually the Earth rotates around the sun, we wind up with that inclination changing the amount of energy by season. So in the northern hemisphere, we get much more energy in the summertime because our radiation is more direct coming in from the sun than it is in the wintertime. So you can see that here. As the Earth is rotating around, here is our December. Most of the energy is directly focused just to the southern hemisphere. Here is the summer, our time. Most of the energy is directly focused right into the northern hemisphere. On the equinoxes, in other words, beginning of fall and spring, it's focused directly over the equator. So, not all energy reaches the Earth. Some of it's scattered, some of it is reflected, and finally, some of it is absorbed. So, because of the law of energy conservation, 100% of all this energy must be accounted for. And those are the 3 things that do it. So what's scattering? Well, ever look outside when it's completely cloudy? A little bit of light coming through, but not a lot. Well, that is because the clouds are scattering the sun's rays back into space. So that is why you're not getting as much heating at that time when it's cloudy. Reflection is also, the brighter the object, the whiter an object is. If you have snow cover in the wintertime, you're going to get a lot of reflection. We call that albedo. It's just the amount of radiation that's getting reflected compared to how much is actually being received. And in the wintertime, snow is about 80 to 90% reflected. So that's why it stays cold when it snows after it a lot of times. All the sun's energy is getting sent back into space. And then we have some that absorbs. There are things like ultraviolet radiation that gets absorbed by chemical reactions. The ozone does that. It protects us. If we didn't have that we had no ozone layer, we would have a lot more cancers and many, many of us would be dead because of it. So this causes a marked warming in the upper part of the stratosphere. We looked at how the temperatures move in each of the troposphere, the stratosphere, and so on. We saw the troposphere got colder with height, while the stratosphere gets warmer. And that is because of this chemical reaction. Here you can see on a satellite image where there's snow, most of it's reflected, and that's what you're seeing when we look down with a visible satellite. You'll notice how dark the lakes are. They absorb a lot more. If you had tree cover, look in right in this section of New York. that is an area with a lot of trees, so that it's not as bright. So here's basically the ratios. About 30% is reflected, another 23% is absorbed in the atmosphere, and another 47% on the Earth's surface. So, and here is a global energy budget because of that. All right, there's another aspect to this. Greenhouse gases absorb infrared radiation. Notice I said infrared. That is not the sun's radiation. That's the Earth. The Earth is infrared radiation. Why is the Earth infrared radiation? Because it's much colder than the sun. So that's the wavelength. Greenhouse gases absorb that. So that means all this ultraviolet radiation that comes from the sun, visible light, hits the Earth, absorbed by the Earth, heats the Earth, and then is retransmitted back into space. When it's retransmitted, it's transmitted in long waves, which are absorbed by greenhouse gases. So greenhouse gases can be anything from water vapor to carbon dioxide to methane. There's a bunch of them. And here you can see water vapor is actually the most efficient. So, interestingly, if you look at water vapor, it's a real interesting way to prove that it has the most impact. Say you lived in a desert, very little water in the air, but you have the same latitude as another area that has a lot of water in the air. The temperatures in that desert will get really hot during the day, right? But they're going to cool off tremendously at night because there is no water vapor in the air to absorb the infrared radiation from the Earth. It just goes back out into space. Now, over an area that has a lot of water vapor, the infrared radiation is absorbed. The nighttime temperatures are a lot warmer. Interestingly, when cloud cover comes in at night, our nighttime temperatures don't drop as much, all because of that infrared radiation getting absorbed. All right, final thing, the calendar curve. Interestingly, they've been increasing faster and faster in the later years here. And you'll notice that during the year, they go up and down. Why is that? Well, they go up and down because photosynthesis goes up and down in the northern hemisphere. So what you're seeing is a record of photosynthesis and how it impacts the curve. But overall, this is a normal temperature. Notice most of the wintertime temperature. This is the green area. This would be the normal high, normal low. Ridiculously cold, but it hardly changes that through most of the winter. Why is that? Because the sun's not coming out. They're getting no sunshine. As soon as the sun starts, you can see it really starts taking off. Now, look at the same thing for Mansfield, Ohio. What do you see here? Wintertime, it's cold. We don't have as much sun. But notice in the summertime, the temperatures are trending upward. So we're winding up with a lot more sunshine, heating from the sun. So confirming what we've just talked about and how the sun's energy is distributed. Finally, I just wanted to give you a quick peek. When I'm looking at satellite, I am looking at a lot of curves. Why am I doing that? Because the air radiates at different wavelengths. So, for example, if I want to look at dusk, I want to look at one wavelength. If I want to look at visible, I can look at a visible blue wavelength, or maybe in the red. I can look at vegetation. It actually emits radiation. I can do water vapor. Maybe I want to look in the top level of the clouds. Or maybe I want something lower down. And finally, I can even do infrared. and all kind of clean infrared to see the tops of the clouds. So you can see how we're utilizing all of this information on radiation to make better estimates and better understanding of what is going on in the three dimensions of the atmosphere. So I hope you got something out of this. Please don't hesitate to